Welcome to the CompTIA A+ Prepcast presented by baremetalcyber.com. RAID stands for Redundant Array of Independent Disks, and it refers to a method of organizing multiple physical drives into a single logical volume for the purpose of enhancing performance, increasing redundancy, or both. The idea behind RAID is to use several hard drives together in a way that provides a combination of speed, fault tolerance, and storage efficiency. Depending on the chosen RAID level, data may be spread across drives, duplicated, or combined with parity information that helps protect against failure. On the A+ exam, candidates must understand the common RAID types and their associated benefits and limitations. RAID 0, also known as striping, divides data evenly across two or more drives without any form of redundancy. Each chunk of data is written alternately to different drives, allowing the system to access parts of the file from multiple sources at once. This configuration improves read and write performance significantly, as the drives work in parallel. However, because there is no fault tolerance, the failure of a single drive in the array results in complete data loss. Striping increases speed but offers no data protection, which is important to remember when evaluating its use. RAID 0 is best suited for situations where performance is the primary concern and data loss is not critical. Temporary working environments, like video editing workstations, game installations, or non-essential testing labs, might use RAID 0 to take advantage of faster data throughput. The lack of redundancy means that data stored in this configuration must either be non-critical or backed up frequently. For this reason, RAID 0 is not recommended for storing long-term data or files that cannot be easily replaced. RAID 1 is a configuration that uses mirroring to copy identical data onto two or more drives. Every piece of data written to one disk is simultaneously written to its mirror. If one drive fails, the other continues to operate with all data intact, providing a high level of fault tolerance. Because the system does not need to recreate or rebuild lost information, recovery is immediate upon swapping the failed drive. However, since each drive contains the same data, the total usable capacity is limited to the size of a single drive in the mirror. The key benefit of RAID 1 is its data protection. This makes it ideal for mission-critical systems where uptime and data integrity are more important than total storage space. Examples include small business servers, accounting systems, or medical office databases. One of the drawbacks of RAID 1 is the reduced storage efficiency, as only 50% of the total capacity is usable. Additionally, write performance is not significantly improved, as each write operation must be duplicated. Still, the redundancy provided makes this configuration a strong choice for users who value reliability. RAID 5 is one of the most popular and commonly implemented RAID configurations. It requires a minimum of 3 physical drives and uses a combination of striping and distributed parity. In this setup, data and parity information are spread evenly across all drives in the array. The parity data is used to reconstruct lost data if a single drive fails. Because the parity is distributed rather than centralized, performance and redundancy are balanced in a way that makes RAID 5 appealing for both enterprise and consumer-level storage solutions. One of the strengths of RAID 5 is its ability to tolerate a single disk failure without data loss. When a drive in a RAID 5 array fails, the remaining drives and parity information are used to rebuild the lost data. This rebuild process can be initiated automatically by a hardware controller or manually through software, depending on the implementation. However, the rebuild process is resource-intensive and can take many hours or even days, especially on large-capacity arrays. During the rebuild, system performance may be degraded, and the array remains vulnerable until the process is complete. RAID 10, also called RAID 1+0, is a hybrid configuration that combines the best features of mirroring and striping. It requires a minimum of 4 drives and consists of mirrored pairs that are then striped across. This setup provides both redundancy and increased performance. Because data is mirrored first, it can tolerate the failure of one drive per mirrored pair without losing data. The striping aspect improves performance by allowing data to be accessed from multiple drives at once. RAID10 offers fast read and write speeds while maintaining robust fault tolerance. When comparing RAID10 to RAID5, several distinctions emerge. RAID10 generally offers better performance and faster rebuild times because the data does not need to be calculated from parity. Instead, it is simply copied from the remaining drive in the mirror. This makes RAID10 preferable for high-performance environments such as database servers or virtual machine hosts. However, RAID5 is more space-efficient, as it only sacrifices the capacity of one drive for parity. The decision between the two depends on whether the priority is speed or storage efficiency. Understanding the difference between RAID0+1 and RAID10 is important when evaluating fault tolerance. RAID0+1 begins by creating 2 striped arrays and then mirrors them. This means that if any drive in one of the striped sets fails, the entire set becomes unusable. In contrast, RAID10 starts with mirrored pairs and then stripes data across those pairs. This structure allows RAID10 to continue operating even if one drive from each mirrored pair fails, making it more resilient under certain failure scenarios. There are 2 primary methods of implementing RAID in a system: hardware RAID and software RAID. Hardware RAID is managed by a dedicated controller card or integrated motherboard chipset. It operates independently of the operating system and generally offers better performance, more advanced features, and lower CPU usage. Software RAID is managed through the operating system using built-in tools. While software RAID can be less expensive and easier to configure, it typically uses more system resources and may lack certain fault-tolerant features found in hardware-based implementations. Configuring RAID using system firmware requires accessing the BIOS or UEFI settings. Most modern motherboards include a RAID mode in the storage configuration section. After enabling RAID, users can enter the controller's configuration utility to select which drives to include in the array, choose the desired RAID level, and initialize the setup. Once created, the array appears as a single logical disk to the operating system. It is important to configure RAID before installing the operating system, as changes afterward may result in data loss or require complete reinstallation. Operating system support for RAID varies by platform. Windows and Linux both include tools for creating and managing software RAID arrays. These tools allow users to combine drives into striped, mirrored, or parity-based volumes. For hardware RAID, the system may require specific drivers during installation to recognize the array. Once properly configured, the operating system treats the RAID array as a single drive, allowing users to format, partition, and install applications as they would on a typical volume. Understanding the interaction between the RAID controller and the operating system is essential for successful deployment. Failure scenarios in RAID configurations can present as unexpected system shutdowns, missing volumes, or dramatically reduced performance. In many cases, the RAID controller or system BIOS will issue a warning that the array is degraded. Degraded status means one of the drives has failed or is no longer responding properly. Users may also observe longer boot times, unusual read or write delays, or storage errors. If a drive has failed, the next step is to replace the disk and initiate a rebuild, which restores redundancy and data integrity based on the RAID level and parity information. Hot spares are unused drives that are installed in the system, but not part of the active array. They are configured to take over automatically in the event of a drive failure. When a drive in the array fails, the RAID controller immediately begins rebuilding the lost data onto the hot spare. This process reduces downtime and eliminates the need for immediate manual replacement. Hot spares are especially useful in enterprise systems where high availability is required, as they provide a quick response to hardware failures without waiting for technician intervention. While RAID offers excellent protection against hardware failure, it is not a substitute for proper backups. RAID protects data from disk failure but not from file deletion, malware, data corruption, or catastrophic events. If a file is deleted or a virus encrypts the array, the replication or parity mechanisms will preserve the damage across all drives. Regular backups to an external location or cloud storage remain essential for full data protection. On the exam, understanding this distinction is critical when evaluating fault tolerance strategies. Calculating usable storage capacity in RAID configurations helps users choose the right balance between performance and storage efficiency. In RAID 0, all drive capacity is usable, but there is no redundancy. In RAID 1, total usable capacity is 50% of the installed drives because each drive is mirrored. RAID 5 allows for the total capacity of all drives minus 1, as that space is reserved for parity. In RAID 10, usable capacity is also 50%, as the data is mirrored and then striped. Knowing how to estimate available storage is essential for selecting a RAID level that meets business needs. Different RAID levels are used in various enterprise scenarios based on performance and redundancy requirements. RAID 5 is often used in file servers, archival systems, and environments where read performance and space efficiency are important. RAID 10 is preferred in high transaction environments such as databases, virtualization hosts, and analytics platforms where both speed and fault tolerance are essential. Choosing the right RAID level requires assessing budget, storage needs, failure tolerance, and rebuild priorities. To summarize, RAID 0 offers speed with no protection. RAID 1 provides full redundancy with reduced capacity. RAID 5 strikes a balance between redundancy and efficiency, and RAID 10 delivers both speed and fault tolerance at the cost of space. Understanding how each level works, how it is configured, and what scenarios it fits is critical for the A+ exam. Candidates should be prepared to interpret RAID layouts, calculate usable capacity, and troubleshoot degraded arrays in both consumer and enterprise settings. Thank you for listening. Please visit baremetalcyber.com for more cybersecurity information, podcasts, books, and more.